Hi everyone, welcome to this channel. Today in this video, we are going to model a helical pulse with a pile cap using a nonlinear finite element approach using vector2. So before going into the modeling, I would like to share some background. Many structures are subjected to cyclic loads such as earthquake events, windstorms, or vehicular traffic loads. During those dynamic loads, sequential application of compression and tensile loads occur in structural elements, especially tall and light structures such as telecommunication towers, transmission towers, wind turbines, or high-rise buildings which are tall and slender. They are particularly vulnerable to tensile uplift loads due to large overturning moments in the structure. So in practice, helical piles are used frequently to resist those uplift force, and helical piles inherently possess high resistance to uplift force. They are fast to construct foundations. Helical piles are commonly connected to superstructures through concrete foundation elements such as pile cap, mat footing, grade beams, where they are terminated with steel plate or brackets as shown in the picture here. So here are three examples of helical piles terminated at a foundation or pile cap using single bracket, double bracket, or studded brackets. In this video, we are going to model a pile cap or a foundation, concrete foundation with helical piles embedded and uplift force is applied. The tensile loading is applied in the structure. So for that, we are going to use finite element software, that is vector2, where preprocessor is a framework class in which we're going to model our structure and apply the loads and everything. And then to analyze and visualize the results, we are going to use post-processor called Augustus. So this is a example of a pile cap with helical piles, and all the physical dimension or properties are taken from a journal paper of Gunnar and Chulwall. So I would like to share the link of this paper in the video below, so you can check out there. So with all this data, for concrete, we have compressive strength, the thickness, helical paths, we have yielding strength, thickness, and also from this all data, we can start our modeling. So let's go into the modeling part. So this is a platform of the framework where we are going to model. So first, we will define our materials. We will start defining by concrete reinforcement because our pile cap is a reinforced concrete. The thickness is here 800 mm. From here in the picture, we can see since here we will model our structure in 2D plane, X and Y direction only. So thickness we have to give. And the compressive strength is 20.7. 1.5 tensile strength. Elastic modulus is 22,005 megapascal. 1.96. 0.15. It is the Poisson's ratio. Thermal expansion coefficient is 10 per degree Celsius. Maximum size of aggregate is 20 millimeter. Add. So here we have added our first material. It is reinforced concrete. Now we have to add properties for helical pile, bracket, steel bracket, and the anchor bolts. So now let's define material properties for helical pile. It is a steel structure. The thickness is 44 millimeter. Yielding strength is 552. Ultimate strength 553. Elastic modulus is 200,000 megapascal. And the Poisson's ratio is 0.3. All the values which are marked as asterisk, they are actually default. There is some default value. If we keep 0, the program will compute this value using a default value, or we can specify as well. So add. And now third our property is, our material is steel bracket or steel plate. The thickness is 260 millimeter. Yielding strength is 345. Ultimate strength is 346, just to keep non-linearity. Elastic modulus is 200,000 megapascal. It's same, Poisson's ratio is 0.3 at. And the last, our structural element is the anchor bolt. We will define its properties. Thickness is 57 millimeter, 724 megapascal yielding strength, 725 megapascal ultimate strength. Elastic modulus is 200,000, and the Poisson's ratio is 0.3 at. In this picture, we can see there are no transverse reinforcement. So here we will keep this data empty, or we will not add anything. If we have ductile reinforcement or transverse reinforcement, we can add it by assigning the data, but we don't have, so we will just delete it. So this is how we define our material properties. So we can define the color of our material. For helical pile, let's define blue. Update. For steel plate, let's define something different. And for anchor, let's define something bright. Update. Okay. So now next we have to define reinforcement. Here reinforcement, it is 15.88 millimeter diameter and 1000 millimeter square area. This is total area of 5 numbers of reinforcement of number 5 rebar. So area is 1000, diameter is 15.88, yielding strength is 414, 600. So everything else we will just keep it default, and let's change the color of the reinforcement. Something add. So once we define our material, now we'll define its region and we'll create a mesh. So first region is our reinforced concrete region. So this is the concrete section. So it is 2100 millimeter long, 600 millimeter in depth or in y direction. So here we will add the coordinates and we will go in anti-clockwise direction. So once 4 nodes are defined, then we will close our structures, but also make sure that you will go anti-clockwise direction, and we'll assign material type, it is concrete material, and define mesh size of 20 millimeter. Add. So now we will create a region for helical piles. So here, this is the helical pile. 140 millimeter is embedded inside, including the steel plate, and below it is embedded in soil. So we are not concerned with the soil, but only this above part. And also it is at 168 millimeter from the edge and 865 millimeter from the center span. So the shear span is at 65 millimeter. So the shear span ratio is 1.68. It is effective shear span by effective date. So our second reason is helical pile shaft. 160, 120. Add. $100 and 220, because it is 160 millimeter. I mean, it has a 60 mm of depth or width, and we only model 200 millimeter, since we are more concerned with embedded depth rather than the depth outside the reinforced concrete. and 120, then we will close it. There's a, okay, we'll cancel it again. Create 160, add 220 because it is 60 mm thick, and 120, add, close, and we'll assign the material type to add, and the mesh size is 20 millimeter. Add reason. Now helical pile is done. We will add a steel plate. 60, 130. Add 60, 120. So these coordinates can be taken from our geometry. So if your structure is different, then it's easy to get those coordinates. So it's material type 3, 20, and 20. Now our first helical pile with single plate bracket is done. Now we will go with another pile, the second one. First coordinate is done. Second coordinate. Third coordinate. And this one is the fourth coordinate. Close it, assign material, and then define mesh size. At the cap, steel plate, not the cap. First coordinate is 2040 and 120. Add 140. Add the second coordinate done. Third coordinate and fourth one. Then close. Assign material type 3 and define mesh size of 20. So we are done with a helical pile and steel plates. Now we will model the anchor bolt. The first coordinate of first anchor bolt. Second coordinate. Third coordinate. Close, and we'll assign the material type 4. And the mesh size, same as before, 20 mm. And also anchor has also a plate at the top, at the bottom, or at the tip. Create another reason. First coordinate done. Second coordinate. Third coordinate. And fourth coordinate. Close. Assign material type. Since anchor bolt has the same material on its shaft and at the plate or bracket, so the mesh size is 20 as before, and then we'll add. So our first anchor bolt is also done, and the second anchor bolt. First coordinate done. Second, third one, and fourth. Close, and then assign the material type. mesh size of 20 and create the plate for the anchor. 1200 and 180 for first coordinate. Make sure we are going anti-clockwise, right? So material type 4 and the mesh size is 20. Add. So here we are done defining our region, and now we will create the truss for our reinforcement. Since effective depth is 540, so first the bottom rebar will be at 60 millimeter from the bottom or x-axis. So this is our bottom rebar, and we assign the property type, and then we add it. And for the top reinforcement, it is first coordinate and second coordinate. Reinforcement type will add. So here we are done defining region, defining truss for our reinforcement, and then at final we will create a mesh. This will take a few moments depending on the size of your mesh. So here we are with the mesh structure in few moments. It won't take too long. See? So our structure is meshed with defined mesh size, and all the regions for different materials are also distinguished with different colors. So now we add mesh to the structure. And now we have to define the boundary conditions. We will define pin support at the bottom of the helical pile shaft because they are embedded into the soil. So we consider or we assume them as a pin support. No restraint. Okay, X and Y add. So we have defined our restraint condition. And also now we will apply uplift load in this anchor bolt. So our load is in the form of displacement. So it is displacement controlled load in Y direction in upward direction. So now these are applied. So here we have our model. We applied boundary conditions and we applied loading in upward direction, that is uplift. And now we will save it and we will run our structure. Before we run our structure, I would like to go in the defined job. In this, when we define job, we will define number of load stages. Here it is already defined previously. So if you are starting a new project, you have to define all these load stages. For example, we applied our load 1, and here the final factor is 3. So it will go up to 3 millimeter. And so initial factor is 0. It will start from 0 with increment factor of 0.1 or 0.01, whatever you want. So it will reach up to the final 3. And to reach this factor, we have to fill total number of load stages. So it is total number is 31. And we have defined our load type. We can define cyclic as well, reverse cyclic, but now we are applying monotonic loading. And also here, we can define concrete models as well. There are many options. We can choose any one. So for now, we will just keep default ones. And then we will run it. So when the structure is running, it will appear in this black screen. And it will take a few minutes to complete this run because it will have 31 load stages. Since I have already run this model, so I will directly take you to the result. So to visualize the result of this structure, then we will click this post processor. It is called Augustus. So this is how Augustus looks like, and we will open our folder, this one. So this is a general overview of our model. It gives a total number of nodes, elements, the concrete model, reinforcement model, everything it gives. It is a summary or general overview of our modeling. And there are many tabs here. We can visualize our results. So here, like there is a cross-section view, converge view or result stiffness matrices, vital signs, cracking informations, displays or cracks, total strains, net strains, element strains, stresses, concrete stresses, reinforcement stresses. So we have a lot of tools here. So basically, I'm more interested in the displacement, load deformation. So here we can see how our this foundation or pile cap deformed when uplift force is applied. So here there are many options: displacement, crack direction, E1 strain, E2 strain. This is a compressive strain, tensile strain, and combined view of this formation and crack. So if I magnify this, for example, if I magnify, yeah, we can see the deformed shape, but yeah, it definitely exaggerates the shape of the deformation. So let's just keep the magnification up to 5, which is normal and realistic. So by shifting our cursor to this curve, or yeah, we can see the deformed shape at different points. And also we can see the crack pattern in each load stage. We can see from this curve. And we can see which material fails first as well. And if we click in combined view, we will see deformed shape as well as crack formation in the structure. If I've set the magnification view, we can see which material first fell. We can see here the steel plate falls first in the structure. So similarly, we can also view a lot of informations here. For example, we can see stresses in, this is the stresses in rebar. So stress, since we don't have any reinforcement, so these stresses are does not seen. So here we can see stress in rebar. We can see here that the rebar at the top yields first. As we see, the green is the maximum number, so the top rebar fails first, and then bottom rebars starts to yield. And also we can see the stresses in concrete. We can see how the stress distributes in concrete by shifting our cursor. And also we can see the stress distribution or direction of stress, how it transfers from load to the support. Yeah, so there's a lot of stress distribution plot. Also strain, we can see strain in Y direction, strain in X direction, shear strain. So we can see at which location there is the highest strain. So you can see that when it fails, there is a strain here at the steel plate. So now I'm interested in to extract this chart. So we can do that by simply view data, and we can copy this data. Simple copy, and we will paste in our Excel file. Since our load is in negative direction because we applied uplift force, so we simply do negative. Let's just keep it 0. And we can plot this chart. And this is the deformation. And here you can see the blue chart is from it is from the paper we have extracted, and the orange chart is the one that we just get from our vector modeling. So this chart, it is extracted from, this is the paper. So we have extracted the chart from this paper, and orange one is we computed from vector modeling. So from here, our model captured quite well the modeling done in the paper, and also we compute the error. So maximum capacity of computed in the paper is for 96 or for 95 kilonewton, and the maximum capacity of our model is 489. So when we compute the error, yeah, it is only 1.1% of error in our modeling. Maybe there are some differences in the parameters because there's a lot of engineering properties or formulas. But somehow it captured quite well the load deformation curve. So this is how we visualize our modeling result in Augustus by using the software post-processor. So this is how we can visualize the results. We model in Formwork Plus. We run our model, we apply loads, and we visualize in Augustus as a post-processor. Thank you so much for your attention. I hope I was able to explain how to model and how to get results from using this software. And thank you so much for your attention. Bye.